Hello everyone, welcome to screencast SC20000. In today's screencast, we are going to demonstrate how to run a throughput test using independent VLANs on the WiNG5 architecture. So let's get started. Our topology consists of a flat network where the RF switch, the wired server, and the AP are on the same single VLAN. The AP is configured to bridge traffic locally. Hence, the RF switch is merely used for management and configuration. The main components of this network topology are the RF switch and the APs, a wired gigabit switch, a wired laptop which serves as a chariot or iPerf server, and a wireless laptop which has the Intel 5300 chipset installed in it. This chipset is capable of transmitting and receiving packets at 300 megabit data rates. You are free to use any other 802.11n capable client as long as it can support 300 megabits of transmit and receive. The software component used in our topology is iPerf or Chariot. The default configuration of the RFS 6000 or the RFS 7000 does not define an IP address on any of the interfaces. Hence, the first thing we need to do is log into the switch and define a static IP address of 192.168.2.100 on the VLAN 1 interface.
To log into the RF switch, the default username is admin, the password is Motorola. We will be prompted to change the password. Let's change it to symbol. We'll hit enable, do a show IP interface brief. This was to check if there is any IP defined on the RFS 7000. The factory default state of the 7000 6000 does not have an IP address, so let's set the IP address by logging into the device itself using the self command. Interface VLAN 1, set the IP address to 192.168.2.100/24. To save our changes, we will do a commit write. Let's check what our IP address is. Show IP interface brief. As you can see, the IP has been set to 192.168.2.100. Let's see if we can ping our wired server, which is 192.168.2.7, and we sure can ping it.
In WiNG5, to create a functional wireless LAN, we need to define an SSID, map an appropriate VLAN to the wireless LAN, and if we would like to secure our wireless LAN, we would have to enable security. To log into the switch, the username is admin, the password has been set to symbol. Now to create a wireless LAN, we will navigate to configuration and then to wireless. We'll click on add to create a new wireless LAN, set the name to moto_ccmp. Let's set the SSID to be the same, which is moto_ccmp, and let's assign our wireless LAN VLAN 1. Now the key thing to note here is everything here on the left hand side has been grayed out. However, once we click OK, we can now navigate to a security policy and define our authentication and encryption types. For this demo, we are only going to be using encryption and no authentication. So let's choose WPA2CCMP. Let's scroll down and set our passphrase to be Motorola. One nifty feature we have here is the show command, which will actually show you the passphrase that has been set here. In our case, it is Motorola. Let's click OK. Our wireless LAN has now been secured with the CCMP encryption. One key thing to note here is if you are running a test in the 802.11n mode, you have to ensure that your encryption is CCMP or it's open. The 802.11n standard does not support WPA2 TCAP or WEP as an encryption type. If you set a wireless LAN to be WEP or TCAP, the radio will downgrade to 54 Mbps. You will not be able to run a test in the 11n mode, and this is as per the standard. Let's click on exit over here. As you can see, our wireless LAN has been set. The SSID is moto_ccmp. It has been mapped to VLAN 1 and the encryption type has been set to CCMP. Now let's commit our changes. Committing our changes will basically write the config onto our running config, and then let's save it to our startup config. In WiNG5, the country code is defined under the RF domain profile. Hence, we will edit the default RF domain profile and define the country code in there. To set the country code, we will first navigate to configuration and then to RF domains. We will highlight the default RF domain that's already been defined on the switch. Click on edit and then go ahead and set our country code to United States. Click OK. Click on exit. As you can see, the country has been set to US. Let's commit our changes and let's save it. In WiNG5, the radio settings and wireless LAN mappings are defined under device profiles. When running a throughput test, it is advised to enable short preamble in the 2.4 GHz radio. The DTIM should be set to 2. Aggregation is generally enabled by default. The channel width should be set to 2040 just to ensure that you can get the maximum throughput. The channel and power should be set appropriately. If the test is run in a small lab, it is advised to set the power to the minimum, maybe about 4 dB. And also the rates should be set appropriately. It is advised to disable the B rates when running a throughput test in the 2.4 GHz band. To map a wireless LAN to a radio or to change any radio settings, we need to edit the profiles. In order to do so, let's navigate to configuration and profiles. As we can see here, we have two AP profiles. One is the AP650 and the AP731. These profiles are created as per the default config. So let's just go ahead and edit these profiles for our wireless LAN mapping and any radio settings we need to change. We will go to radios and check on radio 1, which is going to be our 2.4 GHz radio. Since this is a throughput test, we are going to change those to a static channel. So the first thing we want to do is set the channel to 1. It is not recommended to use 2040 in the 2.4 GHz. Let's set the power to be 4 dB. Since this is a 2.4 GHz radio, we are going to be enabling short preamble to get a boost in throughput. Let's save our settings right here. Our DTIM has been set to 2, which is the desired value. The other thing we want to do is disable any of the 11B rates for better throughput. So we can go here to data rates and choose select. Right now the default rate set includes the 11B rate set as well. Let's just choose GN rate sets just to make sure we can get a good throughput. Click on OK. We now want to map our wireless LAN to the radio. So we go to wireless LAN mapping. As you can see, the wireless LAN that we created is right here, Moto CCMP. In order to map it to the wireless LAN, we'll just highlight that and bring it over to the left hand side. As you can now see, it is advertised on the radio. Let's click OK. Let's just cross check and make sure AMPDU is enabled. As you can see here, it is set to transmit and receive. So we can now click OK, commit our changes and save it. We do the exact same thing for radio 2, where we go ahead and change the channel and power. So for this one, we will set the channel to be 36 plus, which means we are using channel bonding. We are using channel 36 and 40. Set the power to be 4 dB. We do not really care for short preamble, and the DTIM interval is set to 2, so we're good. Let's click OK. Now we will map our wireless LAN as we did with radio 1. Highlight it and bring it over to the left. It's advertised. Click on OK, exit, and commit our changes. As you can see, we've successfully changed the channel and power. The radio 1, the 2.4 gig, has not been set for channel bonding just because we have limited channels in the 2.4 gig RF. And in the 5 gig, we have used channel bonding since there are plenty of channels to play with. Let's exit out of there. Now we will repeat the steps for our 7131 AP. So we'll highlight 7131 profile, edit, go to radio 1, click on edit, set the channel and power. Since we used 1 there, we'll just go to 11 over here. Let's set our power to be smart and set it to 4 dB. Enable short preamble. Since this is a 2.4 GHz radio, DTIM has been set to 2. Disable our 11 B rates, so we only have GN rates. Click OK, click OK, and let's map our wireless LAN.
As seen here, AMPDU is again enabled by default, so we don't have to do anything. We're going to commit our changes and save it. Repeat the process for radio 2. We used 36 plus over there. Let's use 60 plus on this AP. 4, and again DTIM is set to 2. We don't care about short preamble. Let's map our wireless LAN, bring it over here. Okay, exit, commit our changes and save it. So what we've done here now is edited our profile so that they could have the right wireless LAN map to it. We have also successfully changed the channel and power on these APs. In my testbed, I am going to be plugging a 650 and a 7131. As soon as these APs adopt on the RF switch, they will inherit their configuration from their respective profiles. So now let's plug in our APs and see if they show up on our controller. To adopt the APs, simply plug them into the same VLAN as the switch, which is VLAN 1. By default, they are going to go ahead and look for a controller on the same L2 subnet and would adopt over L2 on the RFS switch. One key thing to note here is the AP731 in 5X can now adopt over L2. This was not possible in the 4X world. The AP had to have an IP address and had to be adopted over L3 every single time. But in 5X, there is no difference in the way the AP731 and the AP650 adopt. So we have plugged them into the same VLAN as a switch, and as you can see here, we already have 3 devices. The RFS switch shows up here, which is the device itself. Under there, we can see 2 APs. One AP is the 731, the other AP is the AP650. We are now going to associate a wireless client to our AP. We will give it a static IP address of 192.168.2.200. The first test is going to be an iPerf TCP test, where we are going to be pushing traffic from a wired server to the wireless client. On the wireless client, we will run the iPerf server, which will give us data at intervals of 5 seconds, and the TCP window size has been set to 256. On the wired server, we would configure an iPerf client, which would essentially be pushing packets to the wireless client. Again, this is going to be running a TCP window size of 256. What we see on the screen right now is our throughput results from our test. These snapshots were taken from the wireless client. I used 2 different types of wireless clients. Essentially, we were running the exact same hardware, which was the HP Lightbook 8530W and the Intel 5300 chipset. The only difference being that we had 2 different OSs running on these laptops. As you can see, there is not much difference in throughput. In both instances, we have over 190 megabits of raw TCP throughput, which is kind of expected. With UDP, we expect to see more throughput, so let's see what results we get with UDP. To run a UDP test on the wired server, we are going to be configuring the iPerf client with the -U option, indicating it is UDP, and the -B indicates the amount of bandwidth we want to push, which is going to be 300 megs. The channel does not support 300 megabits of actual throughput or data. However, we are trying to push the limit and see how much can be delivered to the client. We do expect to see at least over 200 megabits per second on a client. On the wireless client, we're just going to have the iPerf server with a -U option, indicating that it is going to be listening on the UDP port. As seen, our UDP overall throughput is over 210 megs in both instances, whether using a Windows XP laptop or whether using a Windows 7 laptop. iPerf is a quick and dirty tool to really measure throughput. It may not be consistent every single time. Your throughput may vary based on various conditions. In this example, I was using a corporate image of Windows XP, which performed really well, but in some instances it may not. So the key thing is to identify a laptop and get consistent results for your throughput. You should now be able to run a throughput test using the RFS 7000 and the adaptive APs, the AP731 or the AP650. The config file for the RF 7000 can be downloaded from this link on your screen. Thank you.